Welcome back to Computer Lessons.
Humanity adopted the decimal system due to the biological count of 10 fingers. Engineering a physical device to distinguish 10 different voltage levels with precision remains a massive challenge. Binary logic simplifies hardware design by requiring only 2 reliable electrical states to represent all possible information. A binary digit or bit represents the smallest possible unit of information in a computing environment. By itself, a single bit can only represent 2 values, often symbolized as 0 and 1. This binary simplicity ensures data remains consistent across vast electronic networks and storage devices. To handle complex information, engineers group 8 individual bits together to form a single byte. This 8-bit structure provides 256 unique combinations for representing data and instructions. It serves as the standard measurement unit for digital storage capacity and system memory. Counting in binary follows a positional system where each column represents a power of 2. Moving from right to left, the values double from 1 to 2, then 4, 8, and 16. This geometric progression allows the representation of any positive integer within a register. Consider the decimal number 13, which translates into the binary sequence of 1101 in a system register. This means the hardware contains 1, 81402s, and 1 single unit. Calculating these values allows the processor to interpret electrical signals as numbers. Binary addition mirrors decimal math, but requires carrying over values more frequent than other systems. When 2 ones are added in a single column, the result is 0 with a carryover bit. Logic gates inside the processor handle these carries at extreme speeds during execution. Negative numbers require a specialized mathematical approach known as 2's complement to ensure efficient processor arithmetic. By inverting all bits and adding 1 hardware, perform subtraction using standard addition circuits. This mathematical elegance reduces the complexity of the physical silicon chip design and logic gates. Decimal fractions are managed through the IEEE 754 standard, which stores numbers in a floating point format. This system divides bits into a sign, an exponent, and a mantissa for scientific precision. Mastering these formats is essential for high-performance computing and complex graphics rendering tasks. While computers thrive on binary, humans find reading long strings of 1s and 0s inefficient. Therefore, developers utilize hexadecimal notation, a base 16 system, to represent binary data in a compact form. Each hexadecimal character represents exactly 4 bits, making memory addresses and color codes easier. Hexadecimal uses digits 0 through 9 and letters A through F to represent values up to 15. A single byte of 8 bits is represented by 2 hexadecimal characters in code. This shorthand is universal in web design system debugging and low-level firmware programming tasks. The processor manipulates these binary values using logical operations such as AND/OR and the XOR function. These bitwise operations allow software to control individual hardware flags and mask specific data bits. They form the logical bridge between high-level code and physical transistor states in silicon. The AND operation outputs a 1 only if both input bits are in the high state. Engineers use this logic to clear specific bits or to check if certain hardware conditions exist. It functions as a digital filter for binary information streams throughout the system. In contrast, the OR operation outputs a 1 if at least one of the inputs is high. This logic is used to set specific bits within a control register without affecting others. It allows flexible configuration of hardware components during the initial system boot process. The exclusive OR or XOR is a unique logical function that outputs 1 only when inputs differ. This property makes it foundational for parity checks and basic encryption algorithms used in communications. It is a critical tool for ensuring data integrity across noisy electrical signal channels. These logical operations occur within the Arithmetic Logic Unit, the mathematical heart of the processing unit. The ALU combines thousands of logic gates to execute millions of these operations every second. This physical hardware is what performs the actual heavy lifting of all computer computation. To represent text, computers map binary numbers to specific characters using standardized tables like ASCII. In the original ASCII standard, the number 65 represents the capital letter A. This mapping allows diverse hardware systems to exchange readable text files and data packets. However, the limited 7-bit ASCII range could not accommodate the vast diversity of global human languages. This led to the creation of Unicode, a universal standard that assigns numbers to every symbol. Unicode ensures text displays correct, regardless of the operating system or regional user settings. The UTF-8 encoding is the most common way to implement Unicode across the modern internet. It uses a variable number of bytes to represent characters, prioritizing efficiency for English text. This flexibility allows a single file to contain multiple different languages and unique symbols. Machine code consists of raw binary instructions that the processor executes direct without any further translation. Each instruction tells the CPU to perform a specific task, such as moving data. This is the most fundamental level of programming possible in any electronic computing system. Writing machine code manually is impossible for modern complex applications due to the massive volume of bits. Developers instead use assembly language or high-level languages like C++ to generate bits. The compiler translates human logic into the binary sequences the hardware silicon understands. Understanding the binary nature of computers reveals why certain software limitations and bugs exist today. For example, integer overflow occurs when a calculation exceeds the maximum value a register holds. This can cause critical system failures if the software does not handle the math error. Memory addresses are managed in binary, determining the maximum amount of RAM a system can access. A 32-bit system can address 4 gigabytes, while 64-bit systems reach astronomical memory limits. This architectural shift was a major milestone in the history of personal computing power. Every image on a screen is a massive collection of binary color data for the GPU. Each pixel consists of red, green, and blue values, stored as binary integers in memory. The graphics processor reads these bits to determine exactly which colors to display. Even complex artificial intelligence models are just performing massive amounts of binary arithmetic in parallel. The speed at which a chip can flip its transistors determines its total processing power. Engineering faster switches remains the primary goal of the global semiconductor industry and research labs. By mastering the binary system, you gain a deep appreciation for the engineering layers of technology. You begin to see the world not as icons and windows, but as electrical logic. This knowledge is the key to unlocking the true potential of computer engineering and hardware. The journey from a single bit to a global network is a testament to mathematical simplicity. In our next technical lesson, we will examine the fascinating world of data compression algorithms. We will show you how we shrink these massive binary strings for fast transmission.
Understanding how binary logic forms the basis of all digital life is a transformative experience. The hardware does not understand your language, but it understands the absolute certainty of math. Which part of binary logic do you find most impressive in its simple yet powerful elegance? If you found this explanation helpful, please hit the like button and subscribe to Computer Lessons. Don't forget to click the bell icon so you don't miss our next class. Thanks for watching, and keep learning.